This video will teach you how to master reduction formula proofs. First of all, what even is a reduction formula? Here's an example. How would you integrate something like this? You could consider the integral of sine to the nx and call that integral in. Then you can prove this recursive formula where in is involved with in minus 2. This is a reduction formula. It's basically writing in terms of a lower form of the integral. You would plug in n equals 7 to get it in terms of I5, then plug in n equals 5 to get in terms of I3, and so on until it's easy to do. But this video is just about how to actually prove the reduction formulae. These are the four main methods. Sometimes you have to use them together. By the way, the fourth one is not that common. The first three are crucial though. On the left, we have some manipulation tricks, and on the right, we have some reasons to do these tricks. It's going to become clear when we do some examples. So let's start with this one. Seeing the x to the n should suggest a power split. So you can take out a power of x squared from this x to the n. And why are we doing that? Well, if you write x squared as x squared plus 1 minus 1, then expand it out and split the fraction, you'll see that you can cancel out the x squared plus 1s, giving us x to the n minus 2 for the first term, and the remaining integral is just in minus 2. So when you have something to some power, you might want to try power splitting. Let's do another example. We have something to some power and it's quite easy to split up. And we can see we should try to cancel with the denominator. So we do a power split of 1, taking out just x minus 1. Then you expand this out, split up the fraction, cancelling the x's, and now we can integrate this first term quite easily, and the second term, if you write it carefully, is just in minus 2. And just like that, we're done. Once again, we have something to some power. So we might want to do power splitting. We do a power split of 2, and that's because we can now use a trig identity. So now when you expand this out, this first term is integratable quite easily. You should be able to do this without u sub. It's just a reverse power rule. The second term is just in minus 2, and just like that, we're done. Let's look at a more challenging example. You have to keep in mind that you want to introduce a lower form of the integral. The only way to really do this is by manipulating inside the argument of the cosine function. So you would do something like this, and then expand out using angle sum identities, so that you somehow introduce the cos n minus 2x. Now that you've introduced cos 2x and sin 2x, you might want to try double angle. I'll leave it to you because I don't want to give it away in this video. Method number 2, basic integration by parts. After this video, you will never have to write u, du, dv, and v ever again. You'll be able to do integration by parts in one line. Here's the new method. Integrate 1, leave 1, minus the integral of integrate 1, differentiate 1. By the way, capital F is just the integral of lowercase f. Integrate 1, leave 1, minus the integral of integrate 1, differentiate 1. Don't forget about differentiating. Example time, x e to the x. We're going to integrate e to the x and differentiate x. Integrate 1, leave 1, minus the integral of integrate 1, differentiate 1. Alright, that was easy. Now ln x, which is technically just 1 times ln x. Integrate 1, leave 1, minus the integral of integrate 1, differentiate 1. So just by remembering a phrase and an animation, you can do integration by parts in one line. When you have a product of two functions, you clearly have two choices for your IBP. Another trick is integrating 1. Let's look at some examples. For this integral, we have something to some power, but we don't want to do power splitting. You can try it, but you'll see that it's not going to get anywhere. And in that case, you would try a different method. We have a product of two functions, so we might want to try integration by parts. We're going to differentiate the 1 minus x to the n and integrate the root x. So integrate 1, leave 1, minus the integral of integrate 1, differentiate 1. When you sub in the bounds for the first term, you just get 0. We want to write this in terms of in and in minus 1 ideally. So we can see the x is very similar to 1 minus x. We can manipulate it as so. Take a moment to check that this is still valid. And then expand it out. And you see clearly we've got what we want. Writing this in terms of I and then rearranging for in gives you the formula we are after. Let's look at a harder example. We have this integral formula we're trying to prove for n equals 2, 3, 4, 5, etc. Let's write the integrand with a negative exponent, and then notice this is just 1 times the same function. So it's actually good for integration by parts, where we integrate the 1 and differentiate the function. This is what you end up with. And now when you see the x squared on the numerator and the x squared plus 1 in the denominator, you should think about doing a plus 1 minus 1. And that way we can cancel with the denominator, leaving us with this. Now we can write it in terms of I. And notice that everything we've done up to this point is valid for n greater than or equal to 1. Okay, so let's rearrange for in plus 1. And you're probably thinking we screwed up somewhere, because we need in minus 1, but we have in plus 1. Well, don't fear, because we can use the shifting trick. Let k equal n plus 1. That will give you this. The previous formula was valid for n equals 1, 2, 3, etc. So this new one is valid for k equals 2, 3, 4, 5, etc. Take a good look at the formula we're trying to prove and the formula we have. They are actually identical. The only difference is we used k, but they used n. Does it actually matter? Well, no, we could use any symbol. So we can actually just dummy variable k to n. In is this formula for n equals 2, 3, 4, etc. And we are done. Manipulation to set up integration by parts is so crucial I've made it a method in itself. Most of the time you manipulate to introduce a term which you can integrate in integration by parts. Sine to the nx is a classic example. It's pretty obvious we have to do some sort of power splitting. We've introduced the sin x term which is easily integratable, so let's perform integration by parts. Integrate 1, leave 1, minus the integral of integrate 1, differentiate 1. After we clean this up, we get a cos squared term, which should immediately suggest 1 minus sine squared. From here on, it's pretty easy. We just expand this out, write it in terms of I, rearrange for in, and we're done. For sec to the nx, we won't do a power split of 1 because sec x is not easily integratable. We'll do a power split of 2 because sec squared x is integratable to tan x. So when we do the integration by parts, we get something like this. When you see this tan squared, you should immediately think of sec squared minus 1. And if you expand this out and simplify, we're going to get our reduction formula. Here is a harder example. The x to the n might suggest power splitting to cancel with a denominator, but that won't really help because it's a square root at the bottom, so you can't properly cancel it. The derivative of a squared minus x squared is minus 2x. So let's do a power split of 1, thereby getting an x, which we can write as minus 2x. Then we can actually integrate this term quite easily. It will just be 2 times the square root of a squared minus x squared. So let's do integration by parts by integrating this term in white and differentiating the other term. If you simplify, you get this. And now we're going to use the square root trick. Basically, we multiply and divide by square root a squared minus x squared, giving us this. We then expand out the numerator and write these in terms of I. And then we're just going to rearrange and we're done. Integration by parts twice in the same direction. Quite a rare one. This is useful when you're integrating f of x times sine x or f of x times cos x, where f of x is not a trig function. E to the x sine x is a classic example. We start off by integrating e to the x and differentiating sine x by doing integration by parts. So that would give something like this. Then we do IBP again on this other integral. We integrate e to the x and differentiate cos x. If we chose it the other way around, we would just go back to where we started. So when you do this, you get something like this. We then rearrange for the integral we're trying to solve, and halving both sides gives us the answer. But let's do an example of this for an actual reduction formula. So we're just going to integrate the sine x and differentiate the x to the n. When you simplify, we have another integral, and we're going to do a similar thing here. We integrate the cos x and differentiate the x to the n minus 1. When you simplify it, you see we've actually got the answer, because this other integral is in minus 2. And now for some crucial advice. First of all, try things. You're not always going to know immediately what method or what manipulation or what trick will lead you to the right solution. You just have to try. You try one method, and if it doesn't go anywhere, you try a different method, and so on.
You have to keep trying different things if it's a hard question. Otherwise, you can't get results. The second thing is practice. This video will put you very far down the track to mastery, but you still have to put in your effort. You have to try as many questions as possible. Just as important is learning from the questions you do, especially if you couldn't do it or you got it wrong. Often there's some general trick you can learn or some general strategy. And now for some challenge problems which I'll leave to you. This is the first one, and this is the second one. In literally 10 minutes and for a whopping $0, I have taught you reduction formulae. So the least you can do is subscribe. I only have 34 subs, so please subscribe. Thank you so much for watching, and I'll see you next time.